Welcome, focused learners, to your next high-stakes operation. Consider this explainer your official mission briefing. You are essentially a secret agent today, and your critical mission, should you choose to accept it, is extracting maximum marks from a highly hostile, incredibly tricky exam paper, and doing it in 20 minutes or less. Today, we are targeting a topic that is absolutely essential for your Cambridge Additional Mathematics IGCSE. We are looking specifically at syllabus code 0606. Our target? Mastering differentiation notation. I'm talking about fully understanding and deploying those specific, precise notations. F' of x, F'' of x, dy by dx, the second derivative, d squared y by dx squared, and of course those really tricky limit notations involving delta x and delta y. Now you might be wondering, why is this specific topic so absolutely crucial? Well, it's simple, because this topic appears in literally every single examination series. It is completely unavoidable. You cannot hide from it. To really illustrate the stakes here, let's take a look at two of our operatives in the field. First, take our operative, Alex. Look at his approach. He overloads his exam paper with raw mathematical facts. He writes this massive, chaotic wall of algebra, just dropping numbers and variables everywhere. But guess what? There is zero analysis. There is zero logical structure. It's just a data dump. On the other hand, we have Sam. Sam's problem is entirely different. Sam rushes the mission. Sam sees the question, completely misses the specific command word requirements, and jumps straight to an unverified conclusion. He wants to get to the finish line so fast that he completely ignores the path to get there. Both of these approaches lead to catastrophic failure in the exam hall. They both end up bleeding red pen marks all over the page. But today, we are going to fix that. We are going straight into the matrix to turn those red marks into green check marks. We're going to build your ultimate exam extraction strategy. Okay, let's dive into this. Why exactly do really intelligent, highly capable students like Alex and Sam completely hemorrhage marks on differentiation questions? It honestly isn't because they don't know basic calculus. Most of you watching know how to drop the power and multiply. The real reason is that they do not understand the subtle, critical language of the examiner. Think of it like a strict grammatical code. When the examiner asks for an exact derivative and you give them an approximation using delta x, boom, you lose marks. When you fail to explicitly label your first derivative as dy by dx, and instead you just write an equals sign floating in the middle of nowhere followed by an equation, boom, you lose marks for poor mathematical grammar. Examiners use differentiation as a filter. They use it to separate the amateurs from the true experts. They are looking for total precision. They are looking for you to demonstrate on the page that you actually understand the fundamental difference between a small change, which is denoted by delta x, and an instantaneous rate of change, which is only found when delta x approaches 0. Alex lost his marks because he didn't define his terms. He just threw numbers at the wall, hoping something would stick. Sam lost his marks because he rushed the conceptual leap from a finite difference to a continuous derivative. Understanding this distinction, really internalizing it, is your ultimate weapon in the exam hall. So, to systematically build your skills, our mission briefing today is broken into 4 distinct sectors. First, we'll cover the core principles. Second, we're diving into the technical methodology. Third, we'll break down critical analysis. And finally, we will look at some highly classified examiner warnings. We've got a lot of ground to cover, so let's get right into it. Sector 1, Core Principles. Before we can even think about executing complex calculations, we absolutely must understand the foundational rules of engagement. If the foundation is weak, the whole structure collapses under the pressure of the exam timer. You see, the theoretical architecture of differentiation notation rests entirely on precise definitions and causal relationships. You literally cannot just memorize a list of formulas and expect to get an A star. You must understand what the notation actually represents in the real world. Examiners use differentiation questions as a multifaceted tool. They are explicitly targeting 3 distinct cognitive domains, which they call assessment objectives. Let's look at the first slice: knowledge and understanding. This is the basics. Do you know that f' of x represents the first derivative? Can you perform the basic mechanical steps of differentiation? Then we move to the second slice, application. Okay, you found the derivative, but can you take that derivative and apply it to find the equation of a tangent line, or the normal to a curve? But here is the secret. The third slice, analysis, is where the top grades are actually decided. This is the battleground. This is where you use the second derivative, d squared y by dx squared, to determine the exact nature of a stationary point. Is it a local maximum? Is it a local minimum? And more importantly, can you justify your reasoning using rigorous mathematical notation? Take a moment right now to mentally evaluate which of our 2 students, Alex or Sam, is attempting to hit all 3 of these cognitive domains. If you think about it, Alex is completely stuck in the knowledge domain. He's just listing equations without any application.
And Sam, he jumps straight to a flawed analysis without showing any of the application steps in between. To extract maximum marks, you must explicitly, visibly move your answer through all three of these domains using precise notation at every single step. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's look at this. This brilliantly illustrates a massive, game-changing insight pulled directly from the principal examiner reports. Listen closely to this quote. Candidates referencing cross-topic connections achieve significantly higher marks. What does this actually mean for you on exam day? It means that top-performing secret agents, the students scoring the highest, never view differentiation in a vacuum. They don't see it as just an isolated math trick. When you see a question about kinematics, your brain should immediately connect displacement, velocity, and acceleration to the notations s, ds by dt, and d squared s by dt squared. When you see a coordinate geometry question about curves, you need to instantly link the concept of the gradient of the curve to the notation dy by dx. The candidates who dominate this exam are the ones who can seamlessly integrate the theoretical principles of differentiation with completely different areas of the Cambridge additional mathematics syllabus. You are essentially building bridges between different mathematical topics, and differentiation notation, that is the exact language you use to build those bridges. Which brings us perfectly to Sector 2, Technical Methodology. This is where we shift from the theory to the precise physical notations you need to deploy on the page to communicate effectively with the examiner. Mastering this table of notations is absolutely vital for your survival in the exam hall. Think of this as your technical loadout. Let's break down these three columns step by step. In column 1, we have the first derivative notations, f dash of x and dy by dx. Now, these represent the exact instantaneous rate of change, or the gradient function of a curve. But here's the trick. Use f dash of x only when the original function is given to you as f of x. Use dy by dx when the relationship is given as y equals something. Mixing these two up doesn't just look messy, it shows a fundamental lack of professional mathematical presentation. It tells the examiner you aren't paying attention to the details. Now, move to column 2, the second derivative, f double dash of x and d squared y by dx squared. I want you to notice the incredibly specific notation here. It is the derivative with respect to x of dy by dx. Let me tell you about a fatal, catastrophic mistake candidates make all the time. They find the first derivative, and to find the second derivative, they just square the whole thing. Put a bracket around it and add a little 2. Absolutely not. That will instantly drop your mark to 0 for that section. You are not squaring the value, you are mathematically differentiating the function a second time. This specific notation is your primary tool for evaluating maximum and minimum stationary points. Finally, let's look at column 3, limits and small changes. This is where things get really interesting. We have delta x, delta y over delta x, and the limit as delta x approaches 0. Delta x represents a small, finite, tangible change. It is an approximation. The absolute magic of calculus, and exactly what examiners are desperately wanting to see you understand, is that as delta x gets infinitely small, as it literally approaches 0, that finite ratio, delta y over delta x, completely transforms into the exact derivative, dy by dx. If an exam question specifically asks you about small changes, you must use the delta notation. Do not use the exact dy by dx notation until the very final appropriate step. It's all about using the right tool for the exact right job. Now we enter Sector 3, Critical Analysis. This is the procedural framework that secures your points by forcing you to explicitly prove your mathematical reasoning to the examiner. Let me introduce you to your standardized 5-step extraction sequence. This is the blueprint for success. I want you to walk through this exact sequence with me. Step 1, deconstruct and extract. Read the command words in the question. Are they asking for an exact value, an approximation, or a coordinate? Extract all the given data immediately. Step 2, select framework. Which differentiation rule applies here? Is it the chain rule, product rule, quotient rule? You need to make that choice explicitly and clearly. Step 3, execute with clear notation. This is where you deploy the exact terminology we just covered. Clearly label your dy by dx. Do not just write an endless, confusing string of equal signs down the page. Step 4, verify reasonableness. This is huge. Does your second derivative actually make sense for the context of the problem? If you are claiming it's a minimum point, your d squared y by dx squared absolutely must evaluate to a positive number. Check it. Don't just guess. Step 5, present with correct terminology. Finalize your answer exactly how the command word requested, ensuring the link to the original context is crystal clear. If our earlier operatives, Alex and Sam, had used this systematic processing, their answers would have been flawless. They would have secured every single mark. Now, to ensure you don't freeze up when the timer starts in the exam hall, we need a memory hack. Look at those 5 steps again. Deconstruct, select, execute, verify, present. I want you to create your own custom acronym for this right now. Lock this sequence into your working memory. Maybe it's DSEVP. Don't skip every valuable point. Or maybe something else. Whatever works for your brain. Write it down, put it on a sticky note, and keep it in your strategic toolkit. Stop scrolling, subscribe to our YouTube channel, Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the mission. We are now entering Sector 4, Examiner Warnings and Common Pitfalls. Pay close attention because these are the exact tripwires pulled straight from the principal examiner reports. The senior examiners have identified exactly 3 specific mistakes that consistently destroy candidate scores year after year. Let's run a quick interactive workshop to conquer them. I'm putting 60 seconds on the mental clock for a data scan challenge. Imagine you are faced with a complex data table in your exam. It's showing the values of x, y, and the gradient of a curve at various points. Your immediate instinct, your agent training must kick in to extract the core trend. Are the gradients increasing? Are they decreasing? Are they approaching 0? If you cannot visually scan that data and immediately connect the concept of a decreasing gradient to a negative second derivative, you are going to lose precious time. You need to read the data like a story. The second challenge in our workshop is finding the flaw in reasoning. The absolute fatal errors here are, number 1, vague answers lacking specific details. Number 2, forgetting to check format and presentation. And number 3, giving answers that are not specific to the given context. Let's look at a flawed sample paragraph from our operative Sam. He wrote, "The gradient is 0, so it's a maximum point. The rate is decreasing." Take a second. Where exactly is the flaw? So the crucial point is that Sam's answer is entirely vague and lacks any notational evidence. An examiner will look at that and give 0 marks. To fix it, to actually get the marks, Sam needed to specify, at this stationary point, dy by dx equals 0. Since the second derivative, d squared y by dx squared, evaluates to be less than 0. The point is a local maximum. Do you see the difference? Precision and context are absolutely non-negotiable. And that leads us to a massive flashing red examiner alert. Principal examiner reports explicitly, repeatedly reveal that candidates consistently confuse key terminology, especially when they are dealing with limits and small changes. You absolutely must always define your terms before using them in extended responses. Let's do a speed writing challenge. If you were asked to draft one perfect paragraph explaining the difference between delta x and dy by dx, how would you structure it? I highly recommend using the Peel framework here. Point, state clearly that delta x is a finite change. Evidence, show the formula for the average rate of change. Explanation, explain that as delta x approaches 0, we find the limit. Link, finally link it all together by stating this limit is the exact instantaneous derivative, dy by dx. If you can articulate that clearly, step by step under pressure, using that exact Peel framework, you are virtually untouchable in this exam. Let's move to the next concept and see how this all builds together. To hit the highest order assessment objectives, you have to progress through 3 distinct framework levels. The lowest level is descriptive. This is where you just list the derivative formula. You write it down and move on. It gets you minimal marks. It shows you memorize something, but not much else. The middle level is analytical. This is where you execute the derivative correctly with clear working, applying notations like f' of x properly. This is good, solid work. But the highest level, the one that guarantees that A star, is evaluative. Evaluative level responses don't just calculate numbers blindly, they interpret them. They evaluate alternative methods, they compare different mathematical approaches, and they make highly justified mathematical recommendations based entirely on the data provided. But exactly what do examiners mean when they say evaluative thinking in mathematics? It requires questioning assumptions. For instance, you can never just assume a stationary point is a maximum just because it looks like one. You have to actually calculate the second derivative to prove it mathematically. It also requires considering different perspectives, perhaps taking the time to verify a complex result using both the quotient rule and the product rule with a negative index, just to be absolutely certain. And above all else, evaluative thinking requires justifying your decisions with concrete mathematical evidence. You extract the raw data from text and tables, process it through your technical methodology, and use it to draw unshakable, bulletproof conclusions. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. We have reached the end of the briefing. You now possess the complete strategic playbook. You understand the notational alphabet, the Peel framework, the time management matrix, and the examiner's own specific criteria for perfection. The only variable left in this equation is you. Here is my final provocative challenge to you. Will you apply this strict method mark strategy and explicitly define your notations in your very next past paper? Or will you let those easy, guaranteed marks slip away into the red? The mission is yours. Execute it perfectly. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep learning, keep analyzing, and I'll see you in the next explainer.